Hey folks, today we're going to take a look at an important distribution in stats. It's called the T distribution. It's actually the last distribution that you will learn about in Business 306. So we've learned about the binomial distribution, we've learned about the normal distribution, and now we're going to take a look at something called the T distribution, or more formally, the student T distribution. The t-distribution is used when sigma is unknown. Let me show you where we're going on this. So the problems that we've been dealing with before, we've said, well, x is normally distributed and it's got some mu and it's got some sigma, and then we can figure out, given a particular x value, what the probability is associated with. And then what we did is we looked and we said, well, what if actually we don't know whether the population is normally distributed? Well, that's actually not a problem because of the central limit theorem. So we had a problem back in the previous video where we're talking about 200 instructors at Red Deer College and the average amount of TV that they watch per week, and it didn't say anything in the problem about it being normally distributed. But because the sample size was large enough, in this case 30 or larger, then we say that it doesn't really matter actually, because if we theoretically took all possible combinations of size 30 for a sample and calculated a mean for each possible sample, then the distribution of those sample means would be normally distributed with a mean equal to the population mean, mu, and a standard deviation equal to sigma, the population standard deviation, over the root of n. And so what we've got here then is that it doesn't really matter whether we know that the population is normally distributed or not. That can be a big question mark. In this particular unit, we're going to say, actually, we don't even need to know what the sigma is, the population standard deviation. Because when you think about it, what we're doing in inferential statistics is we're inferring the characteristics of the population based on a sample. And so if you don't know what the population parameters are, then how do you do that? If you did know what the population parameters are, then of course you are not doing inferential statistics. The whole point of inferential statistics is that you are taking a sample, let's say of 1,000 Canadians, and inferring the characteristics of all Canadians based on that sample. So the point is that we probably don't know what the population mu is or the sigma is. But what we're going to find in this unit is that it doesn't matter. So in other words, we could have a big question mark here. Where we're going to go in the next subunit here, the next few pages after this video here, is we're going to say, actually, you know what? We don't even need to know what mu is here. That we can actually estimate that. That's what confidence intervals are about. Or in unit H, we'll be saying that, well, we can actually hypothesize what a particular mu is and then find out if our x bar, our sample mean, is close enough. So this is actually really good news because it means that we don't really need to know anything about the population. So we're going to take a look here at this part, which is what happens when sigma is not known to you. In that particular case, we're going to use something called a t-distribution. So let's take a look at what that is. Here's our standardization formula, which you've seen before. Z is equal to x bar minus mu. And instead of having sigma over the root of n, we would replace sigma with its best estimate. Instead of the population standard deviation sigma, we would use the sample standard deviation because that's our best estimate as to what sigma is. The problem is that this is no longer a Z distribution. It's not distributed as a Z distribution. It's actually a little different, and it's something called a T distribution. And so the formula then for T is really similar to a Z, except that you're using an S instead of a sigma. Now, let's take a look at what a t-distribution looks like. A t-distribution has many similarities to the standardized normal distribution, so a z-distribution. The first thing is that it looks like a flattened bell curve. So it's like here's a flattened bell curve like that. And it's dependent on something called its degrees of freedom. So a new term for you here. And in our particular course, the degrees of freedom are going to be represented by n minus 1, or calculated by n minus 1. One thing to note is that when we get into Business 307, degrees of freedom may be calculated differently. So when we're dealing with two variables and how they interact, it will be calculated differently. But when we're just taking a look at one variable, one, say, column of data in an Excel spreadsheet, for instance, so one sample, then the degrees of freedom are little n, the sample size, minus 1. Now, this is actually what a distribution would look like for, let's say, n is equal to 2. So that would be 1 degree of freedom. So degrees of freedom would be equal to 1, right? N minus 1, so 2 minus 1 would be 1. So it's really flat like this. It's centered on 0 like that. Let's draw another one. And here's a distribution, which is, now it's supposed to be symmetric, but this would be for, let's say, 4 degrees of freedom. And then I'm going to draw one which looks pretty well normal. Well, it didn't quite reach the middle there, but anyways, it's supposed to. And that looks pretty close to a normal distribution. And so this would be for degrees of freedom equal to 29. So in our particular case, if we're talking about n minus 1, whenever you're talking about, let's look down at the very bottom here, when n is greater than or equal to 30, so 29 degrees of freedom or more, the t-distribution is approximately shaped like a z, a standardized normal distribution. So that's what it is. So it's like a flattened bell curve. It's centered on 0, and it looks more and more normal as the degrees of freedom increase. Hey, just as an aside here, there's nothing particularly magic about the number 30. It's I like to say that there's a lot of good science behind it. It actually had to go back to when they were first creating t-tables, which you're going to see in a moment. Remember, we had the normal table back in the last unit there that we always went to? Well, we're going to have a t-table, which we're going to see in a couple of pages. And it had to do with the fact that the typeset that they were using back about 100 years ago or so only allowed them to go down to about 30 lines. So, and what they said was, well, it's close enough to a Z at that particular point there. And we'll take a look at actually the numbers that we have in a t-table, and you'll see that they are, when we get down to about 29, 30 degrees of freedom, that the t-distribution is pretty normal in shape. So there's nothing really magical about that, but we tend to use that as a general rule here to say that when n is at least 30, you can actually use a dead distribution. Now, here's the thing I want you to know about the way we're going to handle this in Business 306, and if you're continuing on to Business 307, the same way, and that is that the t-distribution is used when sigma is not known. When sigma is known, you use a z-distribution. That's the line of demarcation. It's not to do with the size of the sample. Okay? So although when the sample is large enough, the sample size is large enough, so when n is at least 30, you can use a z-distribution. I want you to use a t if sigma is not known, because that's the reason we use the t-distribution. Again, going back up to the very title here, t-distribution is used when sigma is not known. let's take a look at how we do that. By the way, I do have this discussion right here. And so we're always going to be using that when sigma is unknown, even though it can be approximated by z when n is at least 30. So steps for calculating the probabilities here then is we're going to use something called a t-table. And I've got some cases here on the next page. So I'm going to take you actually to the t-table, and then we'll come back to these cases. So this is a t-table. And it's set up a little bit different than a normal table. So think of the Z table back in Unit N. And the differences are as follows here. First of all, you'll notice that we've got this thing down the side called the degrees of freedom. And as I mentioned here, a t-distribution then is more flattened out when you've got lower degrees of freedom. And as the degrees of freedom increase, then you end up with a tighter distribution, so it actually gets closer and closer to a normal distribution. What that has to do with is the spread of the distribution is a sign of uncertainty. And so a standard deviation, of course, is variation, right? And so the less variation, the more certainty that you have. The bigger the sample, then the tighter the distribution, because the standard deviation is determined by, the width of the distribution is determined by s divided by the square root of n. And so as n increases, then it gets tighter and tighter and tighter. And when n is very small, then you're actually not sampling much of the population, and so there's a lot of uncertainty there, and that's represented by a greater spread there, greater variance in the numbers. Okay, so that's the degrees of freedom here. So what you do then is you take a look at you take a look at the degrees of freedom, which in 306 will always be calculated as n minus 1. And then you would find the particular row. And then you go across, and it's actually set up the opposite kind of way then as a normal table. Remember, in a normal table, what you had on the outside was the z values, and what you had on the inside were probabilities. Here it's reversed. So it's actually showing you here then an area in the tail. So this is 5% in the upper tail. And another difference between this table and the normal table is that, remember, the normal table actually always gave you this area here? It gave you the area from some point down to the middle. The t-table actually gives you the area in the tail from some point up. And the reason for that is that we use the t-table when we're dealing with confidence intervals and hypothesis testing. And you'll see how that fits in terms of calculating probabilities. So what we do then is we find our degrees of freedom. Let's say there's something like, say, 7 degrees of freedom. Oops, 7 degrees of freedom. And this number here, 1.895, would correspond to a t-distribution with 7 degrees of freedom and 5% in the tail. That's what this 5% means here. So this number here would be 1.895. Okay? So that's what we're looking at there. That's what it means there. And that's really similar to a Z table where you've got numbers down here. Remember, the numbers get larger and larger as you get further out. So 1, 2, 3 standard deviations. So this is saying 1.895 standard deviations away from the middle. And that gives you 5% in the upper tail. Let's take a look at a couple of examples here. So I'm just going to erase this. And we'll go and take a look at these cases on the previous page. Now, I'm not going to when we go through probabilities, talk about specific cases like it did in Unit N. Unit N, when we talked about cases, that was to get you used to reading the table. And then I said that when it comes to an exam, you actually wouldn't be able to use a cases sheet. So we're going to mention the cases here, but it's just to show you how to read the table, and we'll just, from that point on, just know how to read the table. But let me give you some examples here. So here's a case where we're looking at the probability that you have a t distribution with 24 degrees of freedom. That's what that little subscript means. And that would have, in our particular case, come from a problem with an n of 25. So a sample size of 25. 25 minus 1, of course, is 24. So it's a t distribution with 24 degrees of freedom. And what's the probability that it is greater than 2.5, or how much of the t distribution is greater than 2.5? Let's take a look at that on the table here. So the first thing that you do is you look for your degrees of freedom. And my degrees of freedom are 24. So right down here. Then what I do is I go across here until I find the closest number to 2.5. And what you'll see is that it's somewhere between here and here. So 2.5 is here. So it's actually the closest two numbers in this case. And then we go to the very top here and we say, okay, that's between 10% and 5%. So 2.5 is between 10% and 5%. Let me show you actually on this diagram here. So what I've got here then is 2.5 is somewhere between 2.452 and 2.7969. That was these guys here. Those two numbers right there. And they corresponded to 10% and 5%. So I've drawn those here, 10%, 5%. So what we're saying is that this area here, from 2.5 up, is somewhere between 10% and 5%. And that's actually how we write it, is we would say that it's, let's see, this is a case 1 over here. So it's somewhere between, oh, hang on. Sorry, it's between 0.5% and 1%. Yeah, I just read that wrong, right? 5 and 10% are over here. So you have to watch your decimal places there, right? That's 0.5% and 1%. Okay, so this is what we've got here then, is that probability is somewhere less than 1%, but greater than 0.5%. And that's actually the answer. Now, one of the things that people don't like about dealing with the t-distribution is they say, well, can't you be more accurate than that? Like when we did the probabilities using the normal distribution, we went to 4 decimal places. And the thing to note here is that don't assume a level of certainty that really isn't there. We're dealing with taking samples and making inferences about the population based on that. So there's a certain fuzziness about this. And so we tend to represent these probabilities then as areas and say, you know, it's somewhere between 0.5% and 1%. And we'll see how that fits in when we get into confidence intervals and hypothesis testing. Let's take another couple of examples here. So case number 2 here says, what's the probability that we've got a 20 degrees of freedom, and we're looking at the t is less than -2. Well, what we do is we say, hey, just like a normal distribution, if we're looking for -2 down, that would be the same as +2 up. Like that. Let me just clean this up with like that. I'll change colors here. So if we're looking for -2 down, looking for that area, that's actually the same as +2 up because of the symmetry of this thing. So that's what I've got down here. So it's always dealing with the upper tail, and so the area from some negative value down is the same as some positive value up. So all we do is we look at our degrees of freedom, which is 20, and we're going to look for the 2. So let's go here, and let's clean this up a little bit, like that. And so we find the 20, and we're going to go across here until we find 2, which is somewhere in here. So we go to the top, and we say it's going to be between 2.5% and 5%, right? Somewhere between 1.7 and 2.086. So it's somewhere between 2.5% and 5%. And that's what we've got down here, right there. That's the answer. Third case here. We're going to look for the probability, let me change colors here, of t with 30 degrees of freedom being less than 1.5. So let's go up here. And we would be saying, okay, let's find 1.5 here, and we're going to look at that point down. So all of this area in here, from 1.5 down. Now, what I want you to notice is, if you take a look at the picture on a t-table, it gives you the area from some point up. So what we're going to find here is, if we're looking at that point down, we want this area here. So if we take 1 minus this area here, that will leave us with this area here going down. Okay? Let me clean that up a little bit there. Show that to you again. If we're looking for this area here, then this would be 1 minus this area here, which is what the t-table gives you. Remember, 100% or 1 is underneath the whole distribution, just like in a normal distribution. So let's take a look at that. What was that again? That was 30 degrees of freedom. So 30 degrees of freedom, and we're looking for less than 1.5. So let's go and just clean this up a little bit. And then we're going to look for 30 degrees of freedom, and we're going to go across until we find 1.5, and it's right in here. And so we go to the top here, and we say that that's somewhere between 5 and 10%. But that's in the upper tail, and so the complement of that would be between 95% and 90%, right? These two would add up to 100%. These two add up to 100%. So if this area here, just looking at the picture over here, is somewhere between 5 and 10%, then this area here would be somewhere between 90 and 95%. And hopefully that's what I got written down here, right there. Okay? And then case number 4 here. And let's just clean this up a little bit here. And so we're looking for the probability that we have a t greater than some negative value, like this. And so let's say we've got minus 2.5, and we're looking at all this area here. It's the same as, and I kind of wrote over top of this here. It's the same here as 1 minus the probability of 2.5 up. So again, you just kind of flip it in your mind. And when you flip it in your mind, it will give you this area here, right? When you flip it, that'll be the upper tail area. And then whatever is left over from 100%, so 1 minus that, will give you the area that you need. So let's look at this example. That will be 18 degrees of freedom. So we'll go down here, and I'm going to look for 18 degrees of freedom. And so that is right here. And we were looking at, what was that again? 2.5. So we're going to come across to 2.5, like that. And you'll see that it's between these two numbers here. So we go to the top, and it will be between 1% and 2.5%. But remember, that's the tail area. And so the complement of that would be 0.975 and 0.990. But, whoops, I wrote 957, not 975. 0.975 and 990. Hopefully that's what I've got as an answer here. Is, oops, right here. Yeah, good. Right there. Okay. You can work through a couple other examples there and see how they work. But I want to work on a real problem now. Show you how this works with the kind of problems that we'll be dealing with. So let's take a look at class exercise number 8, and then I will leave you number 9 for homework. So class exercise number 8 on page E14. It is hypothesized, so I'm giving you a bit of a window into Unit H, our last main unit. It's hypothesized that business students have an average IQ of 100. That is a mu, so it's an average, and it's not talking about a sample here. It's a hypothesis about all business students, and so that is a mu. Later, we'll say that that's a hypothesized mu, but we'll not worry about that right now. Okay, now the next statement is where we start talking about a sample. So we take a sample of 50. So that's not a big N, but a little n. Yields an average IQ of 110. Remember, this is still in the statement about the sample, so that's an X bar, not a sigma. Not a mu. And a standard deviation of 20, that is an S. So that's a sample standard deviation, not a sigma. Assume that IQs are normally distributed. What is the probability of getting a sample mean of 110 or more if the hypothesis is correct? All right, let's go through and see how we would do this calculation here. The first step is that, what do we know about the population? Well, X is normally distributed. We've got a hypothesized mean of 100, and we don't know what the standard deviation is. The population sigma, right? We're given a sample standard deviation of S. So that means that we're going to be using a t-distribution. All right, let's take a look at what that probability looks like. What is the probability of observing a sample mean, an X bar, of 110 or more? So let's draw this out then. So just like we were doing in Unit N, here's a distribution of sample means. Just like the beginning of this particular Unit E, I meant to say. And so we've got something that looks like that. It's normally distributed. It is centered on 100, and we have an x bar value of 110, what is the probability of getting 110 or more? So we're looking for this area right here. In unit H, we'll call that a p-value, the area in the tail. If that area is really small, it means the 110 is significantly higher than the mean of 100, the hypothesized mean of 100, which would give us enough evidence to reject that hypothesis. So I'm kind of jumping ahead, but I want to show you where we're going and why we do it this way. Step number 3 would be to standardize, but this is a t-distribution, and so t is, I always, by the way, I'm going to start using little stars here to show that that's a calculated value. And when we get into hypothesis test, we want to distinguish between what we call a critical table value and a calculated value. So when I put a little star on there, it's a calculated value. All of the z values that we have calculated all through unit n, as well as the beginning of E, are really z star values. And well, I'll just show you how that notation works as we continue on. But here's the formula, is x bar minus mu, that's actually a hypothesized mu, over s, right, because we don't have a sigma, over the root of n. So it's just like the formula that we learned at the beginning of this unit, where we used a z, but there we had a sigma instead of an s. When we don't know the standard deviation, we use s, and therefore it's a t-distribution. So let's plug in the numbers. 110 minus 100 over 20 divided by the square root of, what was our n, 50. And let me grab my book here. 3.54. Okay, let's come up to step number 4 here. Remember, if we were in unit n, the next thing that we would do is we would take a look at a z distribution, except that this is a t distribution. Now, I draw them the same way. So here's a t, but you want to put down the degrees of freedom. So the degrees of freedom here are n minus 1. And n minus 1 then would be 49. So that's n minus 1. So that's 50 minus 1. So 49 degrees of freedom. And this 3.54 is right here. 3.54. So we're looking for that area in here. All right, let's go to a t-table. And the t-table then looks like this. We're going to go to 49 degrees of freedom. Now, in this particular case, you'll see that after 30 degrees of freedom, it goes up by 10 and then 20, and then it jumps up to 120. And then what you'll notice here actually is that this last line here, which in a lot of books they put down as infinity degrees of freedom, are actually just z values. So remember that as the degrees of freedom get higher and higher, then the t distribution starts to look more and more like a z. And so these are actually z values that we have here. Let me give you an example of that. 1.96 is under the 2.5% column. And if you think of how a z table is drawn, this is saying if you got 2.5% here, then that would leave you with 47.5% here, 0.475. Okay? So I want you to think of a z table here. So this would be 0.475. And let's just go back to a z table for a moment. So here's a z table. And what we're saying here then is if we have 2.5% here. And that would leave us with 47.5% here. And if you look up 47.5% here, you get 1.96, right? So 1.96 is associated with 47.5% here and 2.5% in the tail. So let's go back now. To where we were. And take a look at a t distribution. And you can see that under the 2.5% column, you've got at the very bottom 1.96. So the last row of a t-table are just z values. And they're actually common z values that we will use in confidence intervals and hypothesis testing. The other thing that I said was that at 30 degrees of freedom, you'll see that the z values actually, that the t values are actually pretty close to z values here. And you can see that they are all the way down. There isn't much change down here. There is up here. These numbers are a lot different for low degrees of freedom. But as the degrees of freedom increase, then the t looks more and more normal. All right, so getting back to where we were, let me change colors or just do some erasing here for a moment. And we're saying, in our particular case then, let's go down here. We had, 3.54 for 49 degrees of freedom. So let's go down here, and the closest degrees of freedom we have are 40. So what we're going to do is we're going to go across the 40 row, because that's the closest degrees of freedom, until we find 3.54. Now it's actually way down here. So it's off the chart. And if you take a look at the probabilities at the top are getting smaller and smaller as you go, as the t-value gets larger. So what that means then is that 3.54 would actually be something less than that. So less than 0.005. And that's actually how we write it, is we say then that, by the way, I could go and put that this is a case 1 or something and so on. I'm not going to do that. I'm just going to say here that the answer that we've got is the probability of getting a t with 49 degrees of freedom being greater than 3.54 is something less than 0.005. It's further than the smallest percentage column, which is 0.005. That means, back up here, of course, that this probability is less than 0.005. So there is less than a 0.5% chance of getting a sample mean of 110 if the hypothesis is correct. And the hypothesis was that business students have an average IQ of 110. So in hypothesis testing, what we will say here, just to show you where we're going, is we're saying there's only a 0.5% chance of getting that kind of a sample result. So the hypothesis is probably not true. It's actually probably much higher than that. Okay, so that's how we do that. Don't worry so much about the conclusion right now. When we get into hypothesis testing, that's where we'll take a look at that, but this is really what I want you to end at right now, is how to calculate that probability. So what is the probability? It's less than 0.5%. So for homework then, I would like you to do this one, number 9, And we will take that up. And then after that, we get into confidence intervals. So I am going to end the lesson there. Thanks for listening.